Hello, everyone. This is Mr. Couple. Welcome to our first IB Physics SL Year 2 online lesson. Today, we're going to be talking about fossil fuels. We are doing it's called 8.1 energy sources. So, hopefully, you have this handout. You've downloaded it already. If you haven't, just feel free to write it on a separate sheet of paper. I'm probably going to be asking you guys to scan this and send me a copy of your work just at the end, just so I can check down that you completed everything. So, this is Mr. Couple, and joining me today, we have a couple of students. If they want to introduce themselves now, I'm going to let them do that.
Yo, Kelvin here.
Hey, Kelvin.
Hey, this is Alex.
Alex, great to have you here, man.
This is Aryan.
Arian. Anyone
Ryan.
else? Here, Ryan. All right. If you guys want to, I'm going to show you real quick on my screen. We got a bunch of people here in the Discord that are listening, but not everybody has their microphones enabled. But there's a ton of people here. You guys are the champions. This is an amazing showing. I really appreciate you guys coming out today, and hopefully we can salvage and make the most of this situation and learn some physics. So today, this topic is called energy sources, and it's all about where we get our energy from and how there are some good source of energy and there's some bad source of energy. And what I mean by good and bad, I mean like how they affect the environment, but not just that, but also how good are they at producing energy. And so, our entire society runs on energy, and we want to make sure that our energy sources are able to provide enough energy to meet our needs, but then also that our energy sources aren't destroying the environment. The first topic, 8.1, is about the different sources of energy we have, like geothermal, wind, nuclear, fossil fuels like coal and gas. And the second part of this unit is about global warming, we actually call it the enhanced greenhouse effect, and just the way that our burning of these fossil fuels and adding carbon dioxide into the environment and other greenhouse gases, as you know, is contributing to global warming across and large scale environmental destruction in our planet right now. All right, so the first lesson is about the main concept that you need to know about is this thing called specific energy, which is telling you how much energy you can get out of a fuel source per kilogram of that fuel source. And so I'm just going to walk through and just show you guys some problems. We're going to talk a lot about coal today. That's one of the primary fossil fuels that we'll be discussing. And we'll be talking about how much energy you can get out of burning a chunk of coal. And then we'll also be talking about how coal-fired power plants work, which is one of the major sources of electrical production in this country right now. Even though in Kansas things have been changing a lot, like we've been getting a lot more wind power recently, but we still a pretty good chunk, I believe it's around like 30-40% of our energy comes from burning coal. And so I just wanted to dive in and kind of do some calculations with this, and just this is how I'm going to start things off, and we'll just see how things go, and then I can make adjustments from there. Okay, let's start. So the first thing I want to talk to you guys about is this concept called specific energy. So specific energy, if you look at the units, it's joules per kilogram. So essentially, imagine hey, if I had a kilogram of coal, how much energy could I extract from it by burning it? And so that means that coal, if the specific energy of coal is 3.2 times 10 to the 7, that means you get 32 million joules out of burning a kilogram of coal. There's also another quantity called the energy density, and energy density is joules per cubic meter. So that's talking more about the volume. So what volume, if you have a cubic meter, so realize it's like a Minecraft cube. So you have a 1 meter by 1 meter by 1 meter cube. You'd be able to get 7.2 times 10 to the 10th. So that's 72 billion joules out of a cubic meter of coal. So that'd be like in Minecraft, that'd be like a block of coal. So you could say if you burned a block of coal, a 1 meter by 1 meter by 1 meter, you would get 72 billion joules of energy. It's kind of hard to think what the heck is a joule? So think about a joule is that if you wanted to lift a kilogram 1 meter, I should draw a picture of this. So if you have a 1 kilogram mass and you want to lift it up off the ground 1 meter, that would be 10 joules of energy to do that. Since it's MGH, the potential energy. Man, I feel so bad that you guys aren't going to take the IB exam. I can't say you need to know this for the exam anymore. Jeez. So MGH, if this is 1 kilogram, we multiply by gravity 10, and the height is 1 meter, and you get 10 joules. So keep that in mind. If you're generating 72 billion joules of energy, one block of coal could lift this kilogram mass. What would that be, like 7 million or 7 billion meters, which is I don't know how far that is, but that's a lot. That's a crap load of energy. And so this is one of the reasons why coal is such an important energy source for us because you can pack a ton of energy into a relatively small amount of space, which is what the energy density tells us about. All right, so what we want to do here is we want to determine the density of coal. So how many of you guys know the equation to calculate density? If you want to jump in, do you know how to find density? So density, anybody? No, we don't remember.
Is it density equals mass over volume?
That's what it is. It's mass over
I didn't
volume.
look that up, I promise.
It's the mass per volume. So we talk about the mass is how much stuff there is, the volume is how much space the stuff takes up, and the density is how much stuff there is in per unit volume. All right, so if we want to calculate the density of coal, then the way you do that is you can basically write this down. You can say that it's the energy density divided by the specific energy. So if we look at the two quantities up here, you'll notice that if we want to get units of density, we're going to need mass over volume. So we're going to need kilograms over meters, over cubic meters. So the way that we get kilograms over cubic meters is to look at these units here. So we've got per kilograms on this guy and then per cubic meters on this guy. So to get kilograms per cubic meter, which is what mass over volume would be, kilograms per cubic meter, we're going to need to divide by the reciprocal of those two things. So we're going to need to put the specific energy on the bottom and then the energy density on top. And we'll see how that works out. So let me continue with this. So the energy density is 7.2 times 10 to the 10. And we'll write the units down so we can make sure in the end that the units work out. And then we'll divide that by, I'm going to erase all this crazy stuff that I drew over here. And we're going to divide that by the specific energy, which is 3.2 times 10 to the 7. And that's joules per kilogram. So keep in mind what these two, it's really difficult to remember these, but like the specific energy is saying how much energy is there per mass, and then the energy density is saying how much energy is there per space. So there's two ways of saying how much energy is contained within a source. Sounds like someone has a question.
Mr. Keppel,
Yeah.
Alex at least needs to get into the physics classroom so he can join the live stream.
Okay, did he send me a request? Yeah, he did. Okay. All right, you guys get to see behind the scenes of how I add people to the channels. Thanks for letting me know, Aaron. I would have had no idea that was happening. I don't have a dual screen set up yet.
Mr. Keppel.
Sounds like Alex just came in. Yeah.
Yeah. Oh, I've been here.
I meant the other Alex.
Oh, got it. My bad.
What's up?
How long is this lesson?
30 minutes.
30 minutes? Okay. Yeah, I was just asking because apparently our English meeting is at 1:30.
Okay, yeah, you could feel free to drop out, man. Like you don't have to be here. This is just like if you guys want to I'm going to record this anyway, so just figured you guys can come hang out and we could, have some fun. But there's no pressure to like stick around or anything like that.
Bet, okay.
Okay, so we're trying to find the density of coal from the specific energy and the energy density. So once again, the specific energy is how much energy there is per unit mass, and then the energy density is how much energy there is per unit volume. So how much energy there is per amount of material, and then how much energy there is per space it takes up. So we'll continue with this. So if you deploy this in a calculator, you'll end up getting 2.25 times 10 to the third power. And now we just got to figure out what the units are. So you'll notice that since we divided joules in top and the bottom, those will cancel out. But then we have per meter per kilogram. Like what the heck is a per cubic meter per kilogram per weight? Per cubic meter per kilogram. What is that?
Is it kilogram per cubic meter?
Yeah, it's just kilograms per cubic meter. Hey Joel, nice of you to show up.
Hello.
Kilogram per cubic meter. And so that's our density of coal. All right, so this is just whatever. It's like math on a piece of paper. But I thought let's try to make this make more sense. Like let's try to make this more visual. Like we could see it. We could try to imagine it better. So this is a coal hopper train car. Like if you've ever been down to the train tracks, you've seen like tons of these go by. Like just at least here out in Lawrence, like when you look at the trains go by, you just see train after train after train that's just carrying just like tons and tons of coal. So this is about 120 tons of coal that fits inside one of these coal hopper train cars. What we want to do is we want to figure out how many coal train cars would be required to carry an equivalent energy as produced by the fission of 1 kilogram of uranium. So remember back when we did nuclear physics, we calculated the amount of energy that you can get out of fissioning a kilogram of uranium. And we found that it was some like large number, but here's what I'll give you. I'll give you the specific energy of uranium, and then I'll tell you how much 1 ton is in kilograms. So with uranium, a kilogram of uranium will give you a ridiculous amount of joules. So 1 kilogram of uranium, if you fission it through nuclear fission, what is that? That's 70 trillion joules. That's ridiculous. 70 trillion joules for a kilogram. If you compare that to coal, remember coal was 32 million. So you have 32 million versus 70 trillion. So uranium is way more, has a much, much higher specific energy. So we want to figure out if you just have like a little chunk of uranium, like a kilogram chunk of uranium, how many coal trains would be the same amount of energy as that? Okay, so the first thing we want to do is we want to figure out the mass of coal that's in one train. So if one train is 120 tons, we want to figure out how many kilograms of coal do we have. So that's the first part of this problem that we want to do. So the way we're going to do that is by starting out with, let's see, so how did I do this? So I'm taking the specific energy of uranium, so that's 7. Actually, I'm doing this a little bit differently. So I'm going to take the specific energy of uranium, which is 7 point, so how do I put 7? 7 times 10 to the 13, and that's joules per kilogram. And we're going to divide that by the specific energy of coal. So specific energy of coal is 3.2 times 10 to the 7. And let's think about what this is going to do for us. I forgot that I messed this up. I don't need this. All right, man, I'm off my game. This is not how I'm normally doing things. All right, so here's what we know. If we fission a kilogram of uranium, this is the amount of energy that we have, and we're trying to figure out, hey, if each kilogram of coal gives us 3.2 times 10 to the 7, then how many kilograms of coal are we going to need in order to get the same amount as 1 kilogram of uranium? So that's what this ratio sets up for us. So if we get 70 trillion joules of energy divided by 3.2 or 32 million joules for each kilogram of coal, then how many kilograms of coal would this be? And so if you throw that in a calculator, you end up getting that's 2.19 times 10 to the 6th kilograms. So you would need 2 million kilograms of coal to equal 1 kilogram of uranium as far as the energy goes. That's a shocking result. Like that's insane that you could just take 1 little kilogram of uranium and then a million kilograms of coal to get the same as a single kilogram of uranium. So that just shows you that nuclear reactions release ridiculously more energy than chemical reactions do. So now we want to figure out how many cars would that be. So we're going to take that number, so 2.19 times 10 to the 6 kilograms, and we're going to convert it into the following. So we know that there's 120 tons in one car. So I'm going to divide this first, I'm going to convert it into tons, and then I'm going to convert it into cars. So to go to tons, we know that 907, that's the unit conversion I gave you over there, 907.185 kilograms is 1 ton. And so that'll cancel out our kilograms. And then we also know that one ton is not 1 ton, what am I trying to say? 120 tons is 1 car. And so if we do all of this math, we multiply all this together, you end up getting that it's about 20 cars. Which is it's a really fun result because you think about like a baseball of uranium, like this little ball of uranium has as much energy that it can put out as 20 cars full of coal. So that's giving you an idea of what we mean when we talk about specific energy, is how much energy there is per mass. And coal has a really high specific energy, but it's nowhere near the specific energy for uranium and for nuclear processes. All right, how are you guys feeling right now? We're about halfway through.
Pretty good.
Cool.
Yeah, I've been following.
I am also following.
All right, awesome.
Alex, if you're going to talk, you need to speak up.
Aureli sent me a friend request. I will have to reply to that later. There's this really cool XKCD comic with a uranium on a log scale. Let me see if I can show it to you guys real quick because it's a funny comic. All right, here we go. So it says so you can see over here they're showing us the fuel energy density of these different sources of fuel, and you'll notice that uranium has such a high specific energy because it's in the trillions that it just flies off the scale. Like it's just so much more compared to the other ones. So they say log scales are for quitters who can't find enough paper to make their point properly. So if you guys remember what a log scale does is it plots your data in powers of 10. So that way you can sort of squish your scale down and display things. You've probably been seeing a lot of log scales with the COVID-19 data where there's like, millions of cases, or I shouldn't say millions yet, but there's hundreds of thousands of cases across the globe of COVID-19. And so when you're looking at a country that's like just recently had an outbreak, they might only have like a couple hundred cases. You're trying to compare different countries to each other. A lot of people have been putting on a log scale. I think I made a couple posts on Twitter about it as well. Yeah, uranium just has a ridiculous specific energy. It's just insane how much it is, and that's one of the promises of nuclear energy is like we can extract a ridiculous amount of energy from nuclear sources. Okay, question 2. The ton, like how we spelled ton there, that's the British way. The ton of oil equivalent, so that's a unit, TOE, ton of oil equivalent. It's a unit of energy defined as the amount of energy released by burning 1 ton of crude oil. So it's 1,000 kilograms of crude oil. So we use this as, it's kind of a weird unit of energy. Like rather than using like a joule, we're just going to say a tow. A tow is how much energy you get out by burning 1,000 kilograms of crude oil. It's 42 gigajoules. Remember, giga is a billion. So 42 gigajoules is equal to 1 tow. Crude oil has a density of 870 kilograms per cubic meter. So that's not the energy density. That's just a straight up raw density, like how much kilogram takes up what amount of space. Bodhi just died in Minecraft. He forgot to pause his game. Sorry. Okay, question A. Calculate the specific energy and the energy density of crude oil. Okay, so we know that the specific energy, okay, so here we go. So we know that we're going to have 42 gigajoules, 42 times 10 to the 9 joules in how much mass? 1,000 kilograms. And so the key idea here is when you're trying to find a specific energy is you just look at the unit. So we want to know the joules per kilograms. Well, we already know that. We know this 42 gigajoules and we know that it's 1,000 kilograms. And so we just straight up divide those two numbers. So that tells us that the specific energy of, what is this again? Crude oil is 4.2 times 10 to the 7th power. And that's joules per kilogram. Gross. There we go. Finding the specific energy when you already know the joules and you already know the kilograms is just simply dividing the two of them. Now, where it gets more tricky is the density. And so that's why it gave us a density over here, was so we can actually find the energy density. So there's an equation you can use. I'll just give it to you guys. We could talk about why this equation works. I'm not going to derive the equation, but the energy density is the density. So that little symbol right there, it's the Greek letter rho. That's the symbol that we use for density. So if you want to find the energy density, you just take the density of the material and then you multiply by the specific energy. That's supposed to be a subscript. So we already know the specific energy. If you simply just multiply that by the density, it'll work out. And the way you can think about why that works is imagine what the unit of density is. So the unit of density is a kilogram per cubic meter. So if we multiplied a joule per kilogram times a kilogram per cubic meter, you can see that the kilograms would end up canceling and you'd end up with joules per cubic meter, which is the energy density. There's a lot of people coming in and out of the channel. It looks like that other class is starting up. So bye guys, if you're leaving. I guess they can't hear me. I don't know why I just put a B because I said bye.
Godspeed, Mr. Kepler.
Take care, Alex.
I'll come back if you guys are still on.
Okay, great. All right, so now I'm just multiplying these two things together. And I guess I probably should have written down the units, huh? I'm going to rewrite this. If I wrote down the units, we'd more clearly see what's going to happen here. So the density is kilograms per cubic meter. A lot of this topic is not so much equations as much as it is units. Like units are so important in physics, and especially here, all the logical thinking of like how do you get from one thing to another, it's all based on the units. I'm gonna need to turn off my sounds for the people coming and going. All right, so that gives us the energy density of crude oil is 3.65 times 10 to the 10. And now if we look at what units are left over here, so the kilograms times per kilograms cancels out, and we're just left with joules per cubic meter. All right, I feel like I should probably check Discord and see what's going on. Aurelie, okay, sorry about that, Aurelie. You probably had messaged me a long time ago. And then, are you guys talking in here at all? No, okay. Question B, the average American uses 8.5 tons of energy equivalent of crude oil, TOEs, tons of oil equivalent. The average American uses 8.5 tons of oil equivalent per year. Calculate the volume of crude oil this is equivalent to. So if you think about like the average person in the energy they use to drive their car, the energy they use to power their homes, to heat their houses, for everything that an average American does in an entire year, it's 8.5 tons of oil equivalent. So what's the volume of crude oil that this is equivalent to? So like what if you try to imagine it like in terms of like Minecraft blocks, like cubic meters, how large amount of oil does the average American use in a year? And so that's what we're going to calculate now. Okay, so the first thing we want to do is realize that we can create this equation. We can say, we can say that the volume of crude oil, the volume is the energy divided by the energy density. So let's think about why this equation works. So energy is in joules. Energy density is joules per cubic meter. So you can see that what will happen is the joules on top divided by joules per cubic meter on the bottom will end up giving us cubic meters, which is the unit of volume. So this equation works out beautifully with the units. Like I was saying before, we don't really derive or remember these equations. We just look at the units and think about how dividing and combining them together will give us different quantities. All right, so if I do this division, we're going to take the energy, which was 8.5 TOEs. So we're going to do 8.5. But I don't want this to be in TOEs. I want it to be in joules. But because of up here, we calculated up here that a TOE is the energy equivalent of a ton of oil. And we just figured out up here the energy, the specific energy of crude oil is right there. So we're going to take that number. So 4.2 times 10 to the 7, that's joules per kilogram. And we're going to multiply that by 1,000 because we're talking about tons. So I'm going to multiply that by 1,000. So that's the amount of energy that the average American uses in a year. And we want to divide that by the energy density of crude oil. So that's 3.65 times 10 to the 10 joules per cubic meter. I seem to have lost a kilogram here. Oh, the kilogram that I lost is right there. Okay. 1,000 kilograms of oil. Okay, so these kilograms will cancel out, the joules will cancel out, and then we'll end up with per cubic meter, which is just a cubic meter. And so that volume is 9.8 cubic meters. We usually don't use cubic meters to measure the volume of a liquid like oil. We usually use liters or barrels. Maybe you've heard like barrels of oil before. So I thought it'd be fun to just really quickly convert that over to liters. So 1 cubic meter is equal to 1,000 liters. So this volume here, if you imagine like a 2-liter bottle of soda, how many liters of oil does the average American use in a year? Well, it's 9.8 cubic meters. But what is that like? How do you visualize that? I mean, it's 9.8 Minecraft blocks, like 10 Minecraft blocks, but that actually ends up being 9,800 liters of crude oil. So that's a surprising result. I mean, just think like 9,800 liters of oil for your lifestyle to maintain the average American's lifestyle. That's a lot of oil that you have to burn. And then you can start seeing why things like climate change is such a big issue, because if the average person is burning 9,800 liters of crude oil per year, that's nuts. It's so quiet. I feel like I'm talking to myself. Someone needs to say something to ease me here. I'm so uncomfortable. Normally I
I
get to
don't know if
look
it's
out
just me,
across the
but
room.
you're. I don't
What's
know if
up?
it's just me, but you're going like robot mode.
Oh no. It might be Bodhi's watching YouTube and my wife is trying to do a Zoom meeting. Hopefully it fixes. Is it still doing it?
Yeah, kind of.
Dang. I'm sorry. There's nothing I can do about it. I have my crappy free internet. Okay, let me see how I'm doing on time. I have like just a couple of minutes left, so I'm probably not gonna be able to finish this whole page. So I'll probably leave this as an assignment for you guys to finish. I will post the notes though, but I'm gonna keep going for just a couple more minutes here. I think on my clock I got like 3 more minutes that I have to go. So I want to talk about power plants. A power plant produces electricity by burning coal, obviously. The thermal energy produced is used as an input to a steam engine. And so here's the picture here. That makes a turbine turn and that produces electricity. So over here we've got the hopper that's like feeding the coal into the boiler, and it's going to burn that coal and it's going to boil water. And then that boiling hot water goes into this heat exchanger and it spins the turbine. And then the spinning of the turbine is going to generate electricity, and then that's going to get sent out to your homes. This plant, let's say it outputs 400 megawatts. So remember what that means. It's 400 million joules per second that this plant is outputting. And it operates at an efficiency of 35%. So only 35% of the energy that we put in, only 35% of what we put in is actually going to get turned into electricity. This is a pretty normal efficiency for fossil fuels. You usually get a lot of heat loss, like not all of the energy can turn into electricity. You're going to have a lot of heat loss, like radiating out from this boiler. So the typical efficiencies are quite low for fossil fuel burning, especially like in internal combustion engine vehicles and things like that. Question A, calculate the rate at which thermal energy is provided by burning coal. So we want to find out how quickly thermal energy is being provided. So we know that this plant is giving out 400 megawatts. We're trying to figure out only 35% of that is 400 megawatts. So what's the full amount of thermal energy that's being provided? If 400 megawatts is the output of 35% of what we're putting in, if that's what's coming out, then we need to figure out what's going in. So what we're thinking of is like 35% of the energy that we put in is 400 megawatts, is the way that we're thinking about it. So if we want to figure out the energy that we're putting in, we would just need to divide 400 megawatts by 35%. So that means that the energy that we're putting in is 400 times 10 to the 6th watts divided by 0.35. And so that's going to give us 1.14 times 10 to the 9th joules per second. So hopefully that makes sense. Power plants are very inefficient, especially when they're burning coal. There are other sources of generating power that are more efficient, but generally for fossil fuels, you're looking at like in the 30% for your efficiency of energy conversions. So this is a lot of energy that we're going to need to supply. We're going to need to burn an equivalent of 1 billion joules per second worth of coal. So what we want to do here is figure out, well, how quickly are we actually burning the coal itself? So like how many kilograms per second of coal are we actually feeding into this I don't know, reactor, chemical reactor. So the way we're going to do that is we're going to remember a few things from the front. And this, I'm actually out of time now, so I'm just going to finish this problem and then I'll end the video. And then I'm going to have the bottom part down here for you guys to fill out, and I'll ask a few other questions for you to do for a follow-up to this assignment. So we know that the specific energy of coal, this is from the front, was 3.2 times 10 to the 7 joules per kilogram. And then we also know that the power that we need to get from this coal, from burning this coal, the power is up here. It's 1.14 times 10 to the 9 joules per second. Okay, so what we're looking for is the rate at which coal is burned. So that's the delta M over delta T. That's the how quickly, what mass per second of fuel is being burned is what we're looking for. And so if we look at these units over here, you can see that if we divide them in the right way, we can get kilograms per second because we got the kilograms from the specific energy and we've got the seconds from the power, that if we just put this in the right ratio, we can get the units that we want. And so the way that'll be is, since these are reciprocal units, we're going to need to do it in the opposite way that we'd think we would do it. So instead of doing kilograms on top, we're going to put the kilograms on the bottom, so that way it'll inverse the unit. All right, so we're going to put 1.14 times 10 to the 9. That's the amount of energy that we need to get out. And then we're going to divide that by, I guess I should put my units on there. And we're going to divide that by the energy, the specific energy of coal, 3.2 times 10 to the 7 joules per kilogram. And then if you do that division, you end up getting 35.6 kilograms per second. So that's how much. So think about it for a second. It's 35 kilograms. So this little conveyor belt here is feeding 35 kilograms per second of coal into that boiler. That's a lot of coal, guys. That's in each second. So alligator 1, we just sent 35 kilograms into that reactor, and you've got to do that constantly, non-stop, the entire day that this thing is turned on. You have to constantly be feeding it with 35 kilograms of coal per second. That's just nuts when you think about the amount of coal that you need to be dumping into this thing. Okay, I'm finished, guys. So I'm gonna end the video here. I'm gonna stop recording, but I'm gonna stick around in voice chat. So I'll see you guys later. Check in on Google Classroom after this. All right, bye everybody.